We can start now. Okay, hey guys, hi everyone. Welcome to Midnight Sun Hardware Sub Team. My name is Alistair, and like I said earlier, I've been a member of Midnight Sun for exactly a year now. All those who are here today, joining 1:30, I know you guys want to like chill, have lunch, I don't know, go for a party or something on Saturday afternoon. But thanks for being here. And for all those watching the recorded session, you guys like have an advantage because y'all can like chill and take your time. But I'm still going to try and go slowly for those who are like right here. This is our first onboarding session for fall 2021. We're going to be discussing just like basic circuit components. I'm not going to go into anything too heavy, but this is just a little bit as an introduction for most of y'all, hopefully. And I'm going to try to go through this as much detail, like for each component that I do or for each topic that I do. I'm trying to go in as much detail as I think you should be. I don't want to delve too much into one thing because then it'll just feel repetitive and a little extra. Most of the stuff here is stuff that ECE and Tron students will cover in 1B in their first circuits course. So if you're another engineering course, I'm sorry, I don't know how your circuits thing works, but I just hope y'all get a lot from this. But yeah, if you're in 1A or early in 1B, I'm pretty sure you guys wouldn't have covered this much. So I hope you guys really, really learn and take a lot from this. And I hope you'll enjoy this presentation almost as much as I enjoyed putting it together. So let's get started. How do I proceed? Yep, we're super glad to have you here. We're all excited for you. There's a lot of stuff still to be done for Midnight Sun, even though we've been working on this car for, I think, 2 years. Ricky, how long have you been working on this? MS14?
It's around like 2 years.
Yeah, so we've been working on 2 years, so there's still a lot more work that's to be done. So we could really appreciate any and all help. So thanks for being here. We're really excited for you. And yeah, great place to learn skills that employers value. All the stuff that we're going to, at least 99% of the stuff that you're going to do here is stuff that you will probably do in the industry as well. You'll most likely do in the industry as well. These are like the tasks that they give co-ops, they give interns, and they don't want to waste time, training them. So if you just put in your resume like, hey, I learned how to do wiring diagrams, or I learned how to design PCBs, employers just be like, yo, come at me. So it's a good place to like get those skills put in your resume. I actually put Midnight Sun on my resume for my first co-op, and I don't know if he looked at it or not, but yeah, I kind of did it. So you guys can do it. And yeah, have fun. Like I said before the meeting, Midnight Sun has so far been the most rewarding experience of university so far. And I really, really hope that you guys share the same, and please go out, like make connections, talk to people, not only from the hardware sub team, but like go like talk to people in mech firmware, just overall use this as a platform to make the most of the university experience. One thing I would like to point out that I don't want to like put in the presentation is like, please pay attention to this, is you get whatever you put in. So the more time and effort you put into your tasks and learning into how the car works, you yourself will benefit. Speaking from experience, like for me, 1A was pretty hectic. So I kind of did my Midnight Sun tasks like whenever I was free. I didn't actively make time for it. So for me, 1A, I didn't feel like I learned much. But over my first co-op and then 1B, I started like actually making time, like, okay, on this time, I'm going to work only on design, on Midnight Sun stuff. And that's really when I started learning a lot. So really, if you guys, put time and effort, you guys will actually learn a lot more. But don't worry, we are not going to force anyone. If you feel like, oh, I'm feeling overwhelmed with school, we're all students, we're all university, we know how it feels. So just let us know if you're feeling a little overwhelmed, and we'll help you out. Literally everyone is here to help each other out. So relax, guys. And yeah, ask a lot of questions. Nobody's born knowing anything. Please get that in your head. Nobody's born knowing everything. We're all here to learn. At some point in time, we all have that learning moment, and this is yours. So please ask as many questions as you want, and whatever questions you want. Don't undermine yourself by thinking, oh, it's a dumb question. No, we don't, like, even if you don't know anything about circuits, don't worry. That's what we're here to help you out with. Please use this as a learning experience, and you will really enjoy everything good Midnight Sun. Yeah, so this last point was brought to you by Ashmika. Most of you all might see her on Slack. She is a team lead, and she's kind of like everyone's mom who has the answers to almost everyone's questions. So we love Ashmika. She's super helpful. She's nice. And I'm pretty sure she doesn't sleep, because whenever you see her, she's always doing something for Midnight Sun. Yeah. Okay, let's get going. But why? Why do we need to learn about circuits? Well, hardware is all about circuits. So if you didn't get the memo, now you do. Now you do. So everything you did about like, back in high school about batteries, resistors, light bulbs, the hardware is all about that. And that's basically what makes your hardware. Everything else just like stems off of that. Yeah, okay, not like all about, but like 90%, 5% is about making diagrams, block diagrams, another 5% is research. So this is one of the diagrams that we worked on last term. And this was a wiring diagram, which was used for us to know which board connects to which board. So like all this stuff was wiring. And we used this on diagrams.net. Personally, it was a really, really like difficult software to navigate through, but we eventually did it. And I think Nita was the one was in charge for this, or she took like the lead for most of this. Yeah, she's another team lead. And I couldn't find a picture of Nita, so here's a picture of a parrot instead. Yeah, she's always showing off a parrot in stand-up, so here's a parrot. Yeah, Nita's super helpful too. And if you ask her a question on Slack, she replies pretty quickly. And for any wild theories, you can just like go to her and ask her. So yeah, we love Nita's parrot. Okay, let's continue. Power consumption evaluation. So since we're a solar car team, we don't have like unlimited amounts of power. We don't generate as much as electric car or engines would do. So we have to be very careful about which components use the solar energy that we are getting. And because of that, we need to run power consumption evaluation. So we need to know how much power each of the components use. And then we can use that and give it to the strategy team, who basically does all the calculations for us and tells us, okay, this is how much time we can go or how far we can go before we have to start charging the car. And so, yeah, you can also, if you know how to analyze circuits, you will know exactly how much power it's used. And also, this is another thing that employers really like, if you know how to, so they know what circuitry, how much power their circuitry is running, and make everything else based on that. Land that co-op job. If you tell your employer that, oh, I know how to do wiring diagrams, oh, I know how to do PCBs, and be like, yeah, I already know all this stuff, you don't have to waste time teaching me, ooh, you're hired. Just like that. Okay, not just like that, but it improves your chances pretty much. Pass EC 140, MT 120. This is something you're going to get in 1B. You don't have to worry about it now if you're not in 1B. And if you're in 1B, yeah, you guys can thank me later when you guys like get a 90 in EC 140. And to look cool designing PCBs. Oh, PCBs are like easily so cool. Like that's one of the reasons I'm like, oh, I wanted to deal with this kind of stuff. So yeah, to A365.
What are PCBs?
PCBs are printed circuit boards. So let me show you. This is what a printed circuit board looks like. So we have all our circuits, we all have our diagrams, but ultimately, how does that translate into things? We don't have like, if we have small like resistors and capacitors and LEDs, we don't have the LEDs that you see running throughout the things. They're all put down into this one board. Like if I show you the schematics, we have all this. Let me just like, okay, this, and then yeah, all, okay, sorry, let me just, all these sheets you see, all of them, like these are all like compressed into one PCB, a printed circuit board.
You should go to
okay, that makes sense. Thanks.
Yeah.
You should go to the PCB like yeah, that one.
Yeah. But this is just like, oh yeah, this is basically
This is
how
layout.
you design a PCB. Right. This is the layout you make. Yeah,
this is like the layout section for designing the PCB.
Yeah, so before you, like, this is basically the hard work. This is where you make all your connections, all your nets, and all these wires running through. These are actually wires. These are like, what's it called?
Traces.
Traces. There we go. Yeah, I haven't worked on PCB for a while. I've been doing other stuff. So we got traces running through here, but ultimately, this is what it looks like when we get it. And yeah, it's as cool as it looks. All right, then let's go back. There we go. Okay, so I'm pretty sure, like, if you all are familiar, I hope you guys are familiar with these. This is basically what a circuit looks like. I'm sure most of you have done it in high school. This is something that you'll probably be more familiar with from high school. Can I annotate? Let me see. Can you guys see my annotations?
Yes.
Okay, good. I haven't tried this out before. Why did I erase all ink on slide? There we go. Okay, so I'm sure you guys have, y'all know what filament lamps are. They're just like light bulbs that you put in circuits. This is like back in 7th, 8th grade, this is what you do to make circuits. But now you guys are university, you guys are engineers, and we don't use filament lamps anymore. Yeah. So you won't see them. I don't even, so far I've never seen them like even once. Instead, we use LEDs. This is similar for an LED. And for those of y'all who don't know what an LED looks like, this is like what you would put into a breadboard. But when we have our printed circuit boards, you don't have this in particular. You don't have like LEDs looking like this. Sometimes an LED, let me just show you guys. Sometimes an LED can just look like this. Do you all see this little blue thing my mouse is on? Sometimes you could just have an LED like that small. All right. So yeah, that's LED, and this is more of a circuit which you would more like this as opposed to this. This is the kind of circuit that you would see. I got this straight out of like our EC 140 textbook. So this is something that you're more likely to see. And as for what this V and I is, I'm going to get to that soon. Right. So yeah, this is another circuit. That's how complicated circuits can get. So if you don't know your fundamentals, you're going to end up looking at this and be like, what the heck is going on? Like you've got resistors here, and they just randomly throw in a resistor here. You can go for delta Y transformation, but no one likes that because that's a pain. But yeah, don't worry about it because we don't do stuff like this. We don't hate ourselves. We're going to try and make circuits as simple as possible. If you want a certain amount of current, we're not going to throw ourselves into all these kind of configurations. Don't worry. So if you got a heart attack looking at this, yeah, don't worry. We don't do that kind of stuff here. And boom, this is what we actually do. We actually have a circuit looks like this, and this is on the board which I just showed you. Yeah, it may look a little overwhelming for most of y'all, especially if you just come out of high school or even after your first circuits course, you look at this and just like, what is going on? But it's, yeah, once I start explaining stuff, it's going to get a lot simpler, I would say. I mean, you got op amps, resistors, ICs, capacitors, AND gates, MOSFET. I think this is the most complicated circuit we have. It's from a pre-charge board. Yeah, so part of this was designed by James. He's another one of our team leads. And yeah, James was like super helpful. And he doesn't know that I stole his picture from LinkedIn. But yeah, anyways, we love James anyways. It's good. Actually, no, we love all our team leads. They're all super nice and they're all super helpful. And I think I've gone over most of our leads except Micah and Liam. So here's Micah and Liam. I couldn't find a picture of Liam, so I just stole his generic Slack DP. Yeah, so that's two of them. And yeah, actually, no, not just the leads. We love all our members. Yeah, everyone's like super helpful, and they all like spend so much time into Midnight Sun and try and make sure everything works. And they just, yeah, we always make so much progress because of them. So here's all our members. Right, we have 2 Kevins and Kristen, special honorable mention. All right, let's go on. If I forgot anyone's name, I feel sorry, guys, because I just stole this from our active Jira board. Okay, so enough showering love on our team members. Let's get to circuits. All right, so I didn't want to like go without letting you guys know what happens at the atomic level. So right now we have here a copper atom. And oh, it's moving, yeah. And this, of course, you've got your protons, neutrons, and electrons outside. So what happens is this outer electron, known as the valence electron, it leaves the atom, and you end up with just a positively charged ion with a negative electron outside. So this electron is what helps us make our circuits. So in conductors, you have these electrons that just randomly, like, that are available to use. So when we apply like a potential difference, like say, oh, my bad. Here's my annotation. Sorry, guys. Okay, so when you apply like a 5-volt supply, or when you apply energy to this, you're basically allowing the electrons to move. So usually a battery has a positive and negative terminal, right? So because electrons are negatively charged, it'll move towards a positive terminal. So if you have like, if this is your wire and you go and you put in a cell, then you'll have the electrons, they move towards the positive terminal. All right, everyone good so far? Okay, so this is just basically what happens inside. If you guys just know this in your head, I think you must have done this in high school, but it's okay, we can review concepts. If you just know this in your head, you won't be wondering, just then everything else just becomes math, basically. This, if you know this at like this goes on fundamental level, everything else just becomes math. Yeah, some keywords I want, like that's really important for you guys to know. Current, which is the flow of charges, rate of charge movement. So electrons, because they're charged, we say they are the flow of charges, so the flow of charged particles, basically, or yeah, basically the same thing. They measured in amps, and we can measure it using an ammeter in series. I'm going to go over series and parallel configurations later. But I'm sure most of y'all would know. If y'all don't know, just keep this in mind that we measure it using an ammeter in series, and usually refers to conventional current, which is opposite to electron flow. So if electrons move in this direction, wait, my bad. So if you have, oh, sorry, why am I trying to capacitor? So if you have electrons moving, I said most of the positive terminal, right? So if you have electrons moving like this, we actually say that current moves in this direction, because by conventional current, we basic conventional current, which is the flow of positive charges, even though it's not exactly the positive charges that flow, but we just say it's like the flow of positive charges. So whenever we say current, whenever you go like any engineering thing, we will almost never say electron flow. We'll always use conventional current. So this is what you have to concern yourselves with, conventional current. And if you guys want to put into perspective how big an amp is, so this is how big 1 amp of current is. It's 1 coulomb per charge, or 6.242 10 to the power 18 electrons passing at a point per second. Potential difference, so energy supplied per unit charge. So when you apply like a battery or something, you apply a potential difference, which basically means that at this point, the electron has, we would say, has a higher potential than electron at this point, because you can see this is we call this positive terminal, negative terminal. And it basically pushes the electrons. So if you don't have a potential difference, the electrons will just move randomly in all directions. But once you apply a potential difference, you can move them in the direction that you want. And it's measured in volts using a voltmeter in parallel. Again, I'm going to go over series and parallel configurations, but for those of you all who know, this is just going to be like a review, because of voltmeter parallel. Yeah. Resistors. So it's basically implements electrical resistance in a current. Useful, think of it as a rock in a stream, and transfers electrical energy in a circuit heat. So when you have electrons moving through a circuit, right, it's gonna collide with some ions, and when that happens, the collision, like it's gonna like bounce off, and when that happens, that gives off heat or gives off anything. So that's basically resistance in a circuit. When electrons, their path is like impeded, or you're making it, you're slowing them down. That's basically what resistance is. And yeah, so we have resistors, and they transfer electrical energy in the circuit to heat. We also, like LEDs, filament lamps actually heat, but LEDs, they transfer electrical energy to light energy. So we have different components doing different things. You've got motors that transfer electrical energy to kinetic energy. So it depends on what you're doing. But right now, as for resistors, it's just heat energy we're concerned with. All right. Good so far? Okay, let's move on. So yeah, so that brings up more keywords, one of which is resistance. Like I said, measure of opposition of a component to the flow of current is measured in ohms. And we usually, so even if other components, like they make it difficult for current to flow, we usually only use the word resistance for resistors. So when we're talking about other components, we introduce a new word, which is impedance. Now, for a lot of you, this might be a new word, and it's basically, but the Google definition is effective resistance of an electric circuit or component to alternating current. So we usually refer to impedance. So there are two types of current, direct current and alternating current. But usually when we refer to impedance, you can just think of it as resistance. But you have to be careful about not using the word impedance wherever there's resistance, because usually impedance includes the effects of capacitors and inductors. Y'all will learn what capacitors are like slowly, shortly. Inductors, it's not that important, but if you guys really want to know what inductors are, y'all can like ask me questions afterwards, like after the thing, so I can show you guys more in detail. So yeah, so we can't say capacitors have resistance. We can't say inductors have resistance. We say they have an impedance. And you'll often see impedance used interchangeably with resistance because you can kind of think of them as the same thing just to help you understand what impedance is. So yeah, you might wonder, is it another word for resistance just to sound cool? No, it's not. It's actually, you have to be careful about the way you use it. You can use impedance and resistance like interchangeably when you're talking about resistors, but we can't do so when we're dealing with like if we're talking about like certain fixed ICs, which are integrated components we use in our circuit, you will see those. But yeah, we cannot say that they have like very high resistance or very low resistance because they are not resistors. All right. Okay, so this is just a circuit, guys. I want to show you guys. So when we have something like this, these 2 points are at a potential 30 volts higher than these 2 points. And wait, the red circle, I made the yellow circle red, very nice. Yeah, so these 2 points are at a potential 30 volts higher than this, and that is, we can get this from the battery. And usually when we refer to potential difference, we talk about the difference between these 2 points. So the potential difference across this is 30 volts. The potential difference across this is 30 volts. So we don't actually say an absolute thing like, oh, this is actually at 30 volts. No, it's 30 volts with reference to the point before it. So how do we make that all universally referenced? We add this guy here. This is ground. We call it ground, but it actually means 0 volts. So we call like the earth or the like ground, we say that is 0 volts, and then we measure everything relative to that. Okay, good so far? Any questions?
Just put a thumbs up in like for the reactions if you're good.
I'm not checking the thumbs up. I really see you. But yeah, like I said, if you guys have any questions, just drop in like a question in the chat, and then I'll take a pause while you guys ask it. Okay, Ohm's law. Yes, this is very important. This is very important. So this is basically how we can relate voltage with current and resistance. Please note that this works. This is how it is for resistors, mostly for resistors, and I don't think I've come across this for most other opportunities, but most other like components. But for resistors, this is very important to know that V is equal to IR, or if you rearrange the equation, you'll say resistance is equal to voltage divided by current. So R is equal to V over I. This is very important, guys. Please don't forget Ohm's law. V is equal to IR, R is equal to V over I. Ohm's law is super fundamental to anything that we have in circuits. So guys, please don't forget Ohm's law. Okay, checkpoint, just a little bit so you guys remember what we've discussed so far. What does Ohm's law state? Anyone, please put in the chat.
Matthew says V equals to IR.
Okay, very nice. So that's right, V is equal to IR. What does voltage divided by current give you?
Resistance, Ryan.
Okay.
R from Forrest.
Okay. What is resistance in terms of voltage and current?
Forrest says V over I.
Okay.
Addy says V over I.
So as you guys know, these are all mean the same thing. So please don't forget Ohm's law. As an engineer, you cannot forget this. Forget your name, forget your girlfriend's anniversary, forget to take the chicken out of the freezer. I don't care, but guys, please don't forget Ohm's law. All right, let's go on. Right, so this is, I'm just gonna give a little application of Ohm's law and how we can use it in our circuit. So, yeah, so current moves from high potential, low potential. So this is a key point that I don't think I mentioned earlier. So like I said, this one was at 30 volts. So this is at a potential higher than this. Therefore, we have current moving in this direction, right? And this plus and minus, like you can put it now, it's going to be very important in like your first circuits course. But for now, I don't think you're going to need this plus and minus convention, because once you see our circuits, it's going to be pretty obvious in which direction current flows and which direction there's like a potential drop. So you guys don't have to worry about this plus and minus for now, but we know that I is moving in this direction because this is a potential higher than this. Okay, so how do we calculate it? Anyone? How do we calculate the current in this direction and this circuit? Maybe we just put that. Oh, it's 2 and 3.
Anybody?
30 over 5.
Okay.
There we go. Almost 6
30
amps.
over 5.
Okay.
Yeah, it's 6 amps.
Yeah, good job. So, but why is it not moving? There we go. So I is equal to V over R. We got 30 over 5, and that's 6 amps. Good job, guys. Okay, but in reality, this is not what we're going to see in real life, because 6 amps for a circuit like this is way too much. It's 6 amps is like not a safe amount of current to put for this a simple circuit like this. We won't have 30 volts broken down over 5 amps. Yeah, because even in the 6 amps is too much, and as you'll see later, like with power equations, that this will just cause us to lose too much power. So what you can instead see is something that looks like this. At least in our circuits, you've got 3.3 volts as the power source, and your resistance is 5 kilo ohms. A lot of our components you'll see are powered or receive 3.3 volts, and I think all of our resistors use resistance in the kilo ohm range. Mega ohms are like for like millions, like 10 to the power 6 ohms are like for really, really big, for like, I think for ICs and op-amp impedances. Ricky, do you know of any that uses mega ohms in our boards? And
There might be 1 or 2, but most of them are just in like kilo ohms.
yeah. When you think of mega ohms, we usually say like integrated components have mega ohms because they need a very high resistance so that there is less current going through them. But that's not for all, that's only for some ports in some of them. So yeah, most of the resistors that you'll see in our boards are in the kilo ohm range. And this is the amount of current that we have passing through, 0.66 milliamps. Good so far? Right, let's go. Points to remember, yeah, current always moves in closed loops, and current always moves from high potential, low potential. This is, anyone has any questions about this? I don't think I need to explain, but if any have any questions, just let me know. No? Okay, so current always moves from high potential, low potential, as I said. So there's the direction of that push on the electrons, which always causes it to move from high potential to low potential. Yeah, because it's like if you move from a low potential to higher potential, then we have to supply energy, and the whole conservation of energy breaks down, and everyone the whole concept of life breaks down. So yeah, series circuits. Yeah, I want to go over like series and parallel circuits right now. So series circuits, the Google definition is all components are connected end to end, forming a single path for electrons to flow. How I remember this is the same current passes through components. So this current that leaves here, goes here and comes all the way through these resistors, LEDs, resistors, and comes back here. So I put many more components than usually people put when introducing series circuits, just to let you all know that all of these are in series, even though they're like, 6 components here, they're all in series because we have the same current flowing through them. There are no branches or any other paths for them to flow at any point in the circuit. They all just go there. So because of this, we can add up the resistances like 1K, 1K, 1K. And when we add up the resistances, we can get an equivalent resistance. So we have 4 of these 1K ohm resistors. So that gives us a 4 kilo ohm resistor. So basically, this circuit is said to be equivalent to this circuit. You can say it's the same thing. Even though, like, notice that this 2 kilo ohm resistor, like 2 of these are here and 2 of these are here, that doesn't matter. When they're in series, you can just then put them all together. And then you can put these LEDs right here. Don't ask me how, like, when you add up two LEDs, how it works. I don't think there's a formula for that. There's probably something else. But for resistances, this is what you need to know. All right, any questions? Okay, let's proceed. Parallel circuits. Google defines it as all components are connected across each other, forming exactly two sets of electrically common points. So personally, I think this is a really good definition, and this is very important because so we can say that these two resistors are in parallel because the only thing connecting these two is a wire. Like there's no resistor here, or like there's no resistor here, or there's no other component in between. It's just these two are connected by a wire. And because of that, there is no potential drop between these two. So the potential difference across parallel components are equal. So the potential difference between these 2 points is the same as the potential difference between these 2 points because they are in parallel with each other. So yeah, that's what I want you guys. So if I would like put a resistance here, this would not be parallel. Like these two would not be parallel because there is this weird resistance here that is messing us up. Like it's going to make our circuit a little bit more complicated. Not only that, we're going to have different potential differences here. Okay, let me just get rid of this. Okay, so yeah, so this is what we mean by parallel configuration. And just remember that they have to be connected by a wire or something that doesn't have any resistance or use up any potential. And so now we're going to like find out how to get the equivalent resistance of this. So let's break it down by introducing currents. So we have I1, which is I1 enters this point here. And at any given second, you have I1 entering and I2 and I3 leaving, right? So by conservation of like charge, you have to have I1 is equal to I2 plus I3, right? So, but what is I1? What is I2? What is I3? So if you were to call this like V total, we would get V total over R equivalent. Like, so if we were to break this down to a single circuit, we would say that V over R equivalent, which will give us I1, is this V1 over R. Oh, sorry, I messed this up, but yeah. So it's basically this resistance plus this, the current that passes through here plus the current that passes through here. And by Ohm's law, we get this. We can substitute I with this. But then what we also know is that, as I said, potential difference across parallel components are equal. So the V that is here is the same as the voltage that is dropped here. It was the same as the voltage that is dropped here. So V total is equal to V1 is equal to V2. Then we can cancel these out by dividing them all by V2, right? Then we end up with this equation. So this is a pretty important equation for parallel circuits, or how to find the equivalent resistance, which is 1 over R1 plus 1 over R2. And we're going to, and so we simplify the circuit this way. So if you take 1 over R equivalent is equal to 1 over R1 plus 1 over R2, you will get that R equivalent is 833 ohms. So we'll get a power source and then 833 ohms here. That's basically the same thing as this. If you have other components, like if you want to put a voltmeter here and you want to measure, or you want to add like a diode here, then the circuit will change. But if you want to effectively make this circuit with the same resistance, you would make this, if you want to make a series combination of this, you would do this. This is basically the circuit you would get. Okay. Okay, guys. Yeah, I want you guys to like answer this. Is this a series or parallel circuit? Anyone? Both. How can it be both series and parallel? Parallel, but has a series part on it, right? True. Yeah. No definitive answer. Okay, guys. Yeah, it was the heck. Why is this not working? Sorry. Why is this not coming? Yeah, that was a trick question. But basically, we don't say that it is a series or a parallel circuit like that. If you had that thing back in high school, now it's done. We don't say just a series circuit or just a parallel circuit. What we do is we say that they are in series or in parallel with each other. So we say the 10K resistor is in series with this motor and the 2.6 kilo ohm resistor. We don't say that this is a series or parallel circuit. And then we say that these three components are in parallel with the 5K ohm resistor. So we can't say that the 10 kilo ohm resistor is in parallel to the 5 kilo ohm resistor, because it's not. These three components together are in parallel with this 5 kilo ohm resistor. So the potential drop between this 5 kilo ohm resistor is the same as the potential drop between all these three combined. All right. Hope you guys got that. Right. Okay, so here's like our first pause for questions. It's going to be a pretty it might be a lot to take in. So I'm just going to every now and then, but I feel like it's important. I'm just going to pause and hope you guys ask if you guys have any questions. So if anyone has any question, you guys can ask now. Obviously, open the chat for like a quick 30 seconds. Yeah, this was mostly high school review for most of y'all, but if there's anyone who's learned something new today, you guys can ask if you're confused. I'll take a water break.
What we covered may seem really simple for right now, but the next few slides are going to get much more complex compared to what we just learned. It's kind of similar to EC 140, where the first 2 or 3 weeks you're like, oh, this is so easy, why am I doing this? And then the next few weeks they start introducing new stuff and you're like, oh.
Yeah, it gets worse. For all the 1A students, you guys need to know your fundamentals really well, because the exams are just going to be like a very, very unthinkable application of that. And you're just going to be stuck there and questioning whether you even learned anything. So guys, just make sure you all know your fundamentals well. All right. Okay, so I guess that's done. So let's move on to voltage. Why is it doing? Voltage division, right? Oh my goodness. Okay, so voltage division. So there's how would we solve, if you want to find the potential difference across these components, how would we do that? So since it's a singular loop, we know that there's just one current flowing through it, right? God, I hate PowerPoint. There's just, oh my goodness. Sorry guys, I'm just too. So you got this one current flowing through it, right? So let's call that current I. And remember what I said about series and parallel. Since they're in series, your total resistance adds up to 10. So by Ohm's law, your current would be 10 volts divided by 10 ohms. And then your current would be 1 amp. So yeah, current would be 1 amp. And then because of that, you can go back to Ohm's law and find that the potential difference across this would be 8 volts. And the potential difference across this would be 2 volts. Now, if you guys notice something about this, is that the potential difference has been split by the resistance. This one was 8 ohms and there was 8 volts on this. And this one was 2 ohms and there was 2 volts on this. It's split according to the resistance. So what do we get from that? That means the more resistance it has, the more the potential drop is across it. So if ever we want to create a circuit in which we want the potential drop across, suppose we have this resistor, right? And we want say we want to put an LED or something in which we want the potential drop across this to be same as this. We could put an 8 ohm resistor here, put a 2 ohm resistor here, and put this in parallel with this. So that way we would have an 8 volt drop across this. I mean, not necessarily you're going to have to do all calculation and stuff, but if you end up with a potential drop of 8 volts here and you want 8 volts here, then you can connect them in parallel. But if you want, if this has say a 2 volt rating and you have just a 10 volt source, you can do the opposite. You can take a LED and put it here. So the reason why potential voltage divider is important, because it puts into perspective the fact that an increase in resistance would increase how much potential drop you have across it. So this is how I want to introduce it to you guys, because I want you guys to know that because of the current being same everywhere, you end up with the ratio of resistances being this. Because remember, V is equal to IR. So if current is the same everywhere, voltage is proportional to resistance. So that's basically how voltage division would work. So we can we could formally define this equation. And these are the voltage division equations. And this is also really important. Please make sure you guys know this, because it's gonna be really important to know how to, create circuits to get how much voltage you want across it. So this is the general equation for any amount of resistors. So V1 is equal to V total times R1 over R total. And then just for two resistors, R total is R1 plus R2. All right. So we can try and use this equation here. Right. Okay. Yeah, so we can use it here. You guys are I think some of y'all might be a little surprised as to see, what, Alistair, where's the closed loop? Like, no, sorry, I lied. You don't need to put closed loops. Actually, no, I'm just messing. There's actually a closed loop, but in our schematics, you will just see a straight line like this, because what actually is happening is like, you could think of it as a voltage source being connected here and being connected back here. But since we are like engineers, it's no point showing this, because if you just put a 5-volt thing here, it's pretty obvious that we're going to have just current flowing here all the way down. We don't have to show this thing. We just say that's connected to ground here. So it just makes like life easier. And since, you guys are engineers, you have to think like engineers. So you don't want to waste time drawing all this extra loops, taking up extra space on the page. You guys are engineers. So just here are some engineer memes for y'all. God, so lame. That's okay. All right, now let's solve this. So now you guys know how to solve this circuit? Can someone please tell me what's the potential difference, the potential drop across this 10 kilo ohm resistor? Let's find out. So each time it opens, there we go. Yeah, 2.84 volts, because we use this equation 5 times 10K over the overall resistance, which is 10K plus 5K plus 2.6K. Apart from Forrest, can anyone tell me what's the drop across the 5 kilo ohm resistor? .42 volts. Yep, that's what it is. It's just half, because the resistance of this resistor itself is half of the 10K ohm resistor. So you just have 1.42 volts, and then the 2.6K volts would have, or 2.6K ohms would have 0.74 volts. So yeah, so now at least now you guys know that this is the kind of circuits that we'll be seeing around, which is just a straight line instead of having closed, like actual visible closed loops. Okay, here's another one for you guys to do. So if you notice here, the difference is, instead of putting two resistors, I've put in an LED. Now for some of our components like this, we won't really get a resistance in which we have to do voltage division. Instead, we would get like components and we'd get their voltage rating. So we know how much potential difference is dropped across this, right? So then what we get is, we know, so this 3V3 that you see is actually 3.3 volts. Just so I get this, this is actually 3.3 volts. So once again, if you guys still aren't used to this straight line notation, I made this thing a little bit simpler for y'all. Think of there being a voltage source of 3.3 volts. So yeah, how do you go about calculating this? We have 3.3 volts, and then this LED takes up 2 of those, 2 volts from the 3.3. So we just have 1.3 volts left for the resistor. So we have 1.3 volts, and then we have 3.65. It's 3.65 kilo ohm resistor. So because the drop is across this of 1.3, we can use that to find the current, since the same current passes through all these. So that would be 0.36 milliamps. Everyone good so far? Okay. I just want to quickly go over this because there's no way I can explain why this works. If I have to do that, I have to go to like unit level stuff, but these are basically the equations for power. So if you want to find the potential, like the power used up by a component, you have to find the current passing through it as well as the potential difference drop across it. So if you want to find the power of this, you would do 2 times 0.36 milliamps. So that's pretty low, like it's about in milliwatts, but that's okay. Like that's how low current, like some components, the power that they use up. And then if you want to do this, you can do the same thing. You can do 1.3 times 1.3 times 0.36, or instead of finding the current, you can do it directly if you have the potential difference across it and the resistance, which is this equation v squared over r. Or if you don't have the potential difference across it and you just have I and R, you can use I squared over R. Oh, sorry, I squared R. So these substitutions all come from Ohm's law. So like I said, guys, please remember your Ohm's law. Don't forget your Ohm's law. Okay, let's proceed. Yeah, so these are some key points, that key summary that I really want, I want you guys to take from what I just explained. We can choose how much potential drop we want at a component by strategically changing the other components. So yeah, so if we do that, we can divide it however we want. Higher impedances take up more of the voltage available in comparison to components with lower impedance. Notice I said impedance instead of resistance, because when we come into like ICs and stuff and they have very high input impedance, then we remember I said we can't say input resistance because they're not resistors. So yeah, when you say so when we come into those, like when you later go into that, you will realize, hey, it's not the same thing. And you're going to end up realizing, okay, this IC actually takes up most of the voltage and there's barely anything dropping across the resistor. And yeah, voltage division only works if the components are in series. Yeah, guys, please keep this in mind. So if you have like in parallel like this, 2 resistors, we can't use that equation. And if this was like say 5 volts, we can't say like, oh, this R1 times 5 over R1 plus R2. It doesn't work that way. This doesn't work with voltage division. The components that you are dividing the voltage across have to be in series. All right, let's proceed. Okay, dang it. So yeah, so if we want a certain thing and we want keep changing the potential difference across it, does that mean that we have to keep breaking the circuit, taking out the resistor, and then putting back the new resistor, or keep disconnecting the circuit? That's going to be a lot of trouble for us. So we have a nice little component called a variable resistor or a potentiometer, and they're called pot for short. Yeah, sorry, long pot. And they allow us to change the resistance of it has a variable resistance. So if you there's a knob that you can turn around and you can change the resistance of that very thing. There are 2 kinds of variable resistors, potentiometers and rheostat. As far as I know, we don't use rheostats in our circuitry, but if you guys want to know more about rheostats, just hit me up or something and I'll let you know. And yeah, one thing that so I don't know about how it works on PS4 consoles and stuff, but a lot of joysticks use variable resistors. So how this works is the joystick has 2 variable resistors in 2 directions. One is the X direction and one is the Y direction. So when you move the joystick and there is a change in resistance, so we move the joystick, there's a change in resistance. So that the change in resistance causes a change in potential difference, and your computer or your microcontroller will detect this change in potential difference, and it will use that to find out exactly where the joystick is being placed. Yeah, it's actually as cool as it sounds. I found this out a couple of months ago. I'm like, what? So yeah, so potentiometer is actually used in many joysticks. If you guys want to know, I actually have my Arduino board if you guys want see it later on. But yeah, and it's also used in our steering wheel. So we actually use potentiometer in our steering wheel. So like I said, if you move a certain amount, there's a change in potential difference. So okay, this wheel's been moved, and then you can use that to calculate the actual potential difference and find the exact position of the steering wheel. And yeah, here's a small potentiometer. I don't really know what the potentiometer on our steering wheel looks like because I haven't been to the bay yet, but if I do, I'll send a picture on Slack. Okay, any questions so far? Because right now, I hope you guys really understood this, because I'm next slides, it's going to be new for more of you. Like a lot, it's not just high school stuff. I for one didn't learn this in high school, so you guys have to pay close attention to the next part. So if you guys want, like, ask any questions, clarify anything, please do that now. Anyone? All right, or you can like stop the recording. All good. All right, let's proceed. Now we get into the real meat of things. A capacitor. So a capacitor, like by Google definition, is a device that stores electrical energy in an electric field. Now this won't make much sense to you guys, because what does that even mean? But essentially what you guys need to know is that it's basically a small battery that charges and discharges very quickly. So within like milliseconds, microseconds, depending on what resistance value and what the capacitance is, like how big the capacitance is. So capacitance in itself is measured in farads, but because 1 farad capacitance is a huge number, most of our like the capacitors we use at least are in microfarads, nanofarads, and picofarads. Do we use microfarads, Ricky? Do you know? Because I know we use picofarads. I'm just not sure about microfarads.
We do use microfarads a bit, but
Alright.
like it's usually we always just use like nanofarad stuff. Like capacitors are always like really small in the matter. Like the examples in class, or like if we're like designing a board, it's always like very small.
Yeah, it's pretty small. So like you guys know we've got millis and then micro. So it's 10 to the power -6, -9, -12. So as you can like farad in itself is really big of value, and you'll see why we use capacitors as well. So you'll understand why we have such small values. Yeah, so I just want to like show you guys how a capacitor works. So if we apply a voltage source across a capacitor, we have, so a capacitor essentially two metal plates like parallel to each other with like an insulator called a dielectric between them. So what happens is when you apply potential difference, you've got electrons attracted to this positive terminal, right? So the electrons from this plate goes across this through the source and comes and collects here. So because of that, you basically have a deficit of electrons here, and then you've got a lot of like an excess of electrons here. So because of this, there's actually a potential difference between these two plates. And this keeps going on, like these electrons keep moving until there is no potential difference between this plate and this one right here. That means this keeps going on until the potential difference across this is 5 volts. So since this potential, so as a result, there is actually no potential difference between this, like, let me just get the marker, sorry, the pen. So because of that, there's actually no potential difference between this and this. So because there's no potential difference, we don't have any current flowing. And when you don't have any current flowing, it basically behaves as an open circuit or an open switch. So a fully charged capacitor, or as we say capacitor, fully charged capacitor behaves as an open circuit. But note that since they charge and discharge really quickly, like in milliseconds or in microseconds, we just say that a capacitor that's in DC behaves as an open circuit, because it just charges so quickly, we don't even, like, it doesn't even matter. It's almost negligible time for us, like to the human eye. And this is basically the graph of a capacitor charging. So that means initially the potential difference across the capacitor is 0 before you start charging it. Then as you charge, the potential difference increases to 5. So if you notice, like in a battery, you have a continuous 5 volt supply. Like it's not like it goes 5 to 4.6, 4.3, and then it decreases all the way to 0. It goes continuously at 5 for a long time until it just stops working. But a capacitor is not like that. A capacitor will start off at 5, then slowly, gradually give you less and less and less until, like, the charge is gone. All right. This is the graph of capacitor charging. So how would we get rid of the charge on the capacitor? Just as how we would remove the potential difference on a load, we would run a resistor. So how this would work is, because we remember this was positively charged and this is negatively charged. So now we have current. Remember, conventional current, not electrons. We have current flowing in this direction, and it gets discharged through this resistor. So whatever energy was here is being converted to heat energy in the resistor. And this is what it looks like. Like this is, if you were to take the potential difference across the capacitor or across the resistor, this is the graph you would get. So here, because we charge it to 5 volts, this E would be 5 volts. And over time, it would discharge and become 0. Like there would be no potential difference across this. There would be no potential difference across this. And we just have like 2 wires just sitting around. This, if you see this Greek symbol for, so it's called tau. Yeah, it's tau, the Greek symbol tau. And this means time constant. For now, you guys don't need to know what time constant is, but if you really interested, then just hit me up, like let me know after presentation and I'll explain to you guys. To false start. Okay, so I want to show you guys something like real special. Yeah, so something about capacitors and a unique property about them. Ricky, whenever I see false start, I keep thinking of Lord Farquaad. Okay, let's say bye-bye Lord Farquaad and move on. Where did I put that? And here. Okay. Can you guys see? Can you guys see the circuit over here?
Yeah.
Okay. How do I zoom in? There we go. Okay. So right now this yellow line, it shows us so I put in a meter here, and right now this yellow line shows us what the current is. What is the current value that is passing through this? All right. And let's see. So right now there is no current passing through it because it's fully charged. All right. Everyone got that? Once it's fully charged, it's an open circuit. It's an open circuit. There's no current passing through it. But what if I were to reduce the voltage here? Like I would go back to 0. See, notice there is a spike of current because this thing is getting discharged. Like it gets, because right now this is also 0 volts, this is also 0 volts. So it kind of acts like a connection here, and then it gets discharged to this 1 kilo ohm resistor. Now let's put the voltage up again. What do you notice? Like only at that point, at that spike, there's a spike in the current value, and then slowly goes down until there's no current and it's an open circuit. So what if I would just keep doing this with the voltage, like keep changing it back and forth? What do you guys notice? Anyone in the chat, please? What do you all notice about the current when I just keep increasing and decreasing the voltage like this? Look at the yellow line. Alternating. Okay, yeah, it's an alternating voltage, and the current itself is like alternating current. Yeah, but what if I were to keep this straight? You notice that it goes off to 0. But if I were to keep changing it, the current just keeps going back and forth, and it's like as if there is a very small resistance because the current is really current keeps current is always high, either in one direction or the other direction, but current is always high. There's a lot of moving charges. So that's one thing. I hope you guys understand that. So that means in AC, whenever you have a very high frequency of voltage, a capacitor basically behaves as a short circuit. So if in AC you were to replace it with just a wire, like a capacitor in high frequency with just a wire, it would essentially be the same thing if your frequency is high enough. Like if you see here, I'm just changing the current very slowly, right? You can see it doesn't spike as high. So if the frequency is really low, there's not as big a spike. But if I were to keep increasing it, you'd see that current just keeps going back and forth, keeps increasing. So what I want you guys to get out of this is that with a very high frequency, current, the capacitor behaves as a short circuit. Okay, now let's proceed. So Yeah, so DC current and AC current. AC is basically alternating current. So if your voltage goes high and then comes back to zero and goes to negative negative V and then again increases back. So this is alternating current for those of you who don't know. And now why this is important is, so do you guys know how radios work? It basically sends a like radio stations, they send a signal onto an antenna, and that antenna vibrates. And we pick up those signals, like that antenna vibrates, and that antenna is basically a circuit. And then that vibration is picked up, and then the current that passes through it is processed. That's how radios work. But all around us, we have radio waves. And especially in a moving car, we've got a lot of like parts that are vibrating, a lot of parts that are sending out electromagnetic waves. And what these will do is these will mess with the electrons in our circuit. So we are essentially trying to send a DC circuit, but then because of the noises, it's called noise, all this unnecessary electromagnetic radiation, it's called noise. And that causes like vibrations in our circuit, right? So because of that, we have and yeah, because of that, it's going to cause issues. Like we're going to end up having voltages that we don't want instead of like the voltage that we send out. So in that way, capacitors are like super useful, because if we were to like put a capacitor, strategically place a capacitor, we can use it to filter out high frequencies and low frequencies. Yeah, I think I should have put in an example here about how it does that, but hopefully I'll get to do that later. But essentially what I want you guys to get is this: because capacitors in very high frequency AC behave as a short circuit and other one is open circuit, we can make use of that advantage. Capacitor with potential different applied across the same as for a long time as in like 1 or 2 seconds, because it has a very small charge and discharge times. That behaves as an open switch. And a capacitor in AC behaves as a short circuit. So instead of like, so if you have a resistor like that, and you have a capacitor here, like that's ground, and this is your this is like something you want to apply voltage to. Let's call this a load. Okay. If it's at very high frequency, that means instead of going here to this resistance, it'll just short off and it'll just go into the ground here. If it has high frequency and AC current, and only the low frequency waves that we send or the DC that we send, that's what passes through here. Did you guys get this? Like, it's not a very good diagram, but I hope you understand what the gist of this is. Because we send our low frequency signal, and that, because capacitor behaves an open circuit, it cannot pass through here, but it can, so it goes directly to the load. But if we have a high signal, again, it will because the high signal, this is a short circuit. It's a path here that it want to go. So current wants to use the less resistance path. So instead of going to the load, it'll just get like, the capacitor will block it off and it'll go through the capacitor and down to ground. All right. Okay. So yeah, this is another way. Like if you forget whether it allows a DC or AC, you can think of this diagram. So if you try to send DC through it, it blocks it off. But if you send AC, it goes back like down inside the capacitor and comes around. Yeah. So we say low frequencies because we don't really deal with ideal DC like it's straight. There's always going to be some kind of oscillation. But if it's a really, really low frequency, we kind of treat it as DC. I mean, I'm not exactly 100% sure how it would work with like low frequencies, there's any changes, but for all, like at least until 1B, you learn to treat low frequencies as DC. Yeah, I actually stole this slide from Nita. She did onboarding last year. So thanks, Nita. Right. So this right here is one of this. I stole this from our pedal board schematic. As you can see, we have a lot of capacitors here. They all do the same thing. So if you have high, high frequencies, they all like leave the path and go to ground instead of bothering us here. All can go to ground instead of bothering us here. Right? Hope you guys like got this part. I'll pause and take any questions. Anybody? I guess getting all this, like, is it fine. If you guys is stuck, anything doesn't make any sense at all, please let me know. I don't be babbling off for no reason.
Do you ever use them in series?
Capacitors in series, we don't usually have the need to use them as series until we are actually charging, because it doesn't serve the purpose. But in all our boards so far, we only use capacitors for this purpose. I don't think we have any other purpose for them to use in series. I mean, you could use them in series based on what you have. So I think for us in 1B, we had design project, and in that we ended up using a capacitor in series because we want to detect the salinity of a solution, and we put a control, and we put a capacitor across the control and a capacitor across the salt water, and we tried to see that. In that situation, we use capacitor as series because, you'd have, again, it serves as potential divider. Like you could say the potential drop across this capacitor is less than that. So in a situation like that, you would use a capacitor in series. But as far as I know, I don't think we use capacitors in series here, because we don't want to store and then release that energy immediately in series. Instead, we instead use them as parallel to, get rid of unnecessary noise. But yeah, you can use it in series. We don't usually use it.
Oh, okay. Thanks.
Yeah, no problem. Anyone, any other questions? Do you guys notice something weird about this schematic? Anyone? Or do you all notice anything about the schematic at all? Like, do you all recognize anything from this? I'll give you guys a hint. What's that? Yeah, do you guys know what this is? Anyone? All right, no problem. Okay, so this right here is an op amp. This is a very, very, very important component. I guess, I don't know, but this is very important. You'll see this everywhere in all the schematics, and you're going to find out what they do. So operational amplifiers or op amps. So this is what it looks like on design. If you look at an actual op amp, it looks exactly like any other, small board or small circuitry or small IC on a board. It doesn't look any different. But when you draw a schematic, it looks like this. And basically, we have a total of 5 inputs. One is the non-inverting terminal. It's called non-inverting terminal, inverting terminal, the output, VCC and VEE. So usually instead of VCC, we say V plus, and we say this is V minus. But I didn't want to confuse you guys, because when you get an actual op amp, y'all won't, it won't be called like V plus and V minus. It's we said VCC and VEE. So just for this slide, I'm going to call this V plus and this V minus. We good? Okay. So how it works is, it basically does this particular math. So the output voltage will be A times V plus minus V minus. So this minus this times A. And what is this A? A is a very big value. It's around 10 to the power 5. So usually when we have like voltages in like 2 volts, 3 volts, 10 to the power 5 seems like a very big number. So for simplicity's sake, we say A approaches infinity, because it's a really, really big number, 10 to the power 5. Yeah, another thing I'd like to mention is op amps are one of those components that have very, very high input impedance. So it's in like, you can say that basically there is a resistor here that's in mega ohms, but that doesn't affect anything inside. There's no actual, I don't know if there's an actual resistor in there, but it has a very high impedance, which means that by Ohm's law, I is equal to V over R, right? So because of this very high impedance, the current that goes to this is almost zero. We usually say it has like zero current, but if it has zero current, then there's no voltage, but it's very, very small, like in microamps, nanoamps, like it's very, very small. So we say the current approaches zero. All right. So yeah, so that's one thing I just want to give you guys an example of what one of those components that have very, very high input impedance. Okay, so if you guys think about this, A is really high and like almost infinity. So you're telling me if we put like 5 volts here and 0 volts here, we could essentially get like 10 to the power 5 volts of output, like infinite voltage and infinite energy. Like literally every single Marvel movie would cease to exist if we did that. And then Doc Ock's like Spider-Man 2 itself would like raise itself hell. So yeah, like are you telling me that every single Marvel villain would have got his dream? Sadly, no, that's not how it works. And Doc Ock did not die for nothing. We are literally stopped by 2 little party poopers, and they are called VCC and VEE. That means our voltage, like our output voltage, is bounded between these 2 values. And usually VEE is less than VCC, right? So if you have like 12 and 12 connected to the op amp and it goes to ground, no matter what you put, like you put here like 30 and you put like 0 here, 30 minus 0 is 30 minus 0 times 10 to the power 5 will be like, I don't know, 30,000 volts. But because of VCC, it'll just be blocked off at 12 volts. All right. And this is a graph for you guys to like see. So VCC minus or VEE, it's the same thing. Yeah, so it gets saturated here. And the slope A is 10 to the power 5. So I think you guys can see what this means. It means that if we have very small voltage discrepancies only, you can maybe find an intermediate value. Like if your voltage difference, like V plus minus V minus would be like 0.001 volts. Maybe then you would find something that has an output of 3 volts, right? Like, but we can't like get that. So it's more often than not, we'll either only get VEE or VCC. And I think this will really help you guys to see why, let me just go back to the previous slide. Oh goodness, there's so much stuff. I think this will really help you guys see why we use all these capacitors here to filter out that noise. Because if we end up allowing that noise to pass through these op amps, then we're going to run into a lot of trouble, because we're going to have voltages, instead of giving us 12 volts or ground, we're going to have intermediate, because that's how op amps work. So I hope you guys can now appreciate why we're using capacitors here before the op amps, so that we don't end up, sending in voltage and getting voltage values that make absolutely no sense when they should be either 12 or like ground. Okay. Right. I hope you guys got that. I was so excited for that one thing. All right. So here are some common configurations of how we use op amps. So we use it as a comparator. So if you want to tell like the difference between these 2 voltages as a comparator, I want to use an example straight from our boards. And this is an op amp that will help us make sure that our, the temperature inside our board, the temperature is not too high. So we have a thermistor, an NTC thermistor. So basically an NTC thermistor is a component whose resistance decreases as temperature increases. Okay. That means if the temperature is really high, we have a low resistance and there's a low voltage here. So when there is a low voltage here, like there's a reference voltage. So if our reference voltage is greater than our thermistor voltage, then we would have 3.3 volts going in. That's how it's connected here. Like I want you guys, so this on the right shows us what our VCC is. So if the reference voltage is greater than the thermistor voltage, we would have 3.3 volts going and telling us that, oh yeah, it's too hot, it's over the temperature. But if our thermistor voltage is less than this, then our output would be 0 volts. And then we know, okay, yeah, it's not over temperature, like the temperature is right. Okay. Any questions about this? Okay, let's proceed. Buffer amplifier. So this is another one of our reasons of one other thing that we use op amps for as a buffer amplifier. So So basically what it does is this V in will be the same as V out. Now you all might be asking, why do we need to use an op amp? Like, why can't we just like connect the 2 points? Now the reason we use an op amp is because remember how I said op amps have a very, very high input impedance. So because of that, we have like small current, like we have very little current going through here. So suppose if you were to put like a resistance here, then like instead of just, if you were to connect this directly to connect this directly to V out, we would have like current, a high current here, and we would lose some power because this is resistor. But instead, if we were to use an op amp, then we don't have a very high current because it has a very high impedance. So there's very little current going through here, and we'll just have the desired voltage coming out. We're not losing any power. So this really helps us save in like with like power consumption. Okay, so that's one of the things we use, buffer amplifier. And then we can also use a Schmidt trigger. So you could use it, but we don't usually like go for Schmidt triggers. It forces input signal to high or low, and just make sure that noise, like if there is a noise or something, it doesn't change voltage without going through a certain threshold. And we don't like use amplifiers. We just go straight for the ICs. We don't concern ourselves with the op amps. Yeah. So now it's time to like summarize all we did like after that. All this new stuff. We can use impedances, component voltage ratings to have a component take a certain amount of voltage. So this is basically what I want you guys to get from the entire voltage divider section that I went over. And then the second point is capacitors. So they can charge and discharge quickly, allowing them to filter out unwanted noise. And that's exactly what we use most of our capacitors for. And yeah, op amps are super badass and can be used as comparators, as buffers, as Schmidt triggers. But more like, I think these two are of more concern, comparators and buffers, because Schmidt triggers you'll see them along the board. We use Schmidt triggers a lot, but we usually get them as components themselves instead of using an op amp. And yeah, that's about it. So for next week, so this is like really important, guys, please, because if you guys want to know what's going on next week, I really highly suggest you'll watch these 3 videos on our hardware channel. Oh, sorry, on the Midnight Sun channel. There's workshop part 1, part 2, part 3. If you guys want to know where it is, it's on our Midnight Sun solar car team on our channel. Just go and check it out there. It's hardware A365 workshop part 1. I'm going to post these slides later on Confluence, so you can guys check it out if you want, or if you want like get started immediately, just take a note of this. And yeah, once like please make sure you guys do this, and otherwise next week's session you guys won't understand anything that's going on. So please get these two. I think it's a total of 45 minutes, like both videos combined. So yeah, get this done. And usually we get homework at the end of the session, but I don't want to give. So guys, I want you guys to prepare for this. And yeah, and if you guys are done with this and you're still bored, you can watch the knowledge shares to learn more about the car. I'm pretty sure we've covered literally everything on those knowledge shares about how our car works and what each thing does. And yep, thank you for sticking around. It was quite the roller coaster of emotions, but thanks for sticking around, guys. And I really hope you enjoyed presentation. Hope you all stick around with Midnight Sun. And if you have any questions and you want to like ask after recording is done, feel free now. Thanks, guys. Okay, Ricky can stop the recording now, please. Thanks.